we have seen that the mathematical model is a complicated boundary value problem, much more complicated than what you would get in conduction. Let's think about how the ANSYS Fluent Solver will solve it for us using the finite volume method. So in the process, I'm going to give you a whirlwind tour of the finite volume method, focusing on the big ideas and particularly the errors introduced and how we can minimize those errors. If I briefly go back to the framework of what's inside the black box, I'm moving from talking about the mathematical model to talking about how it's going to be solved using the finite volume method. And in the finite volume method, you take the domain and you divide it into multiple control volumes or cells. So this is the domain we have. It's a rectangle. And let's say we divide it into chunks as shown over here. So I've shown 18 little chunks over here. In reality, we'll have thousands or now even millions of little chunks. And each of those chunks is called a cell, or you can think of it as a control volume. It's similar to elements in the finite element method. And then you say you reduce the problem to determining velocity, pressure, temperature values only at cell centers. You say, you know what, it's really hard to find these variables everywhere. Instead, I will find them at the cell centers, and I'll mark off a few here just to make that idea concrete. So you solve our determine our four variables at these cell centers. And you can think of the value at the cell center as an approximation for the average value over that cell or the control volume. And if instead of finding, let's say instead of finding the temperature, at everywhere, so as a function of R and Z, what you're doing is finding, in this case, 18 values of temperature. Solving differential equations to find unknown functions is really hard. Finding discrete values of temperature and other variables is not as hard if you have computers and software. And this process of going from, to determining only discrete values rather than functions is called discretization, and it's really the heart of any numerical method. And then if I'll use interpolation of self-centered values to determine values at other locations within a cell. So for instance, if I want to know the value over here, which is halfway, along this face over here, I'll just interpolate the neighboring cell center values, and the simplest case would be just taking an average of those two values. Okay, so you have discretization and you have interpolation. So then the crux of the problem is, how do I find velocity, pressure, temperature at the cell centers? By the way, this is the cell center flavor of the finite volume method. You also have the node center or the vertex center method. Now Fluent uses the cell-centered method. So to find the cell center values, you start with your boundary value problem and you derive a system of algebraic equations and cell center values. And you do that by doing a control volume balance for each cell. And I dig deeper into this in the big ideas in computational fluid dynamics in my online course at EDX. And each algebraic equation relate a cell center value to its neighbors. So if I do mass conservation for this cell, so that would be my control surface, I would relate this cell center value to these cell center values. And this would be velocity if I do mass conservation. For instance, this cell center value will not be involved and so on, and this cell center value. Which means that you get, if it's a matrix, if you think of it as a matrix, it's a sparse matrix. And then once you have the algebraic equations, you can invert it to find the cell center values of our velocity and pressure. And there's a complication here that these equations are nonlinear, so we have to linearize them. I'll get to that. And then once we have the cell center values, we can determine, the temperature everywhere, wall shear, etc., through post-processing just by interpolation or interpolation and differentiation. Another way to look at it is shown over here, which gives you an overview of discretization, and then there's linearization because our algebraic equations are nonlinear. So the starting point that I showed you was the differential form of the governing equations plus boundary conditions, i.e. a boundary value problem. Now you can go to the integral form of the governing equations and boundary conditions, and so the exact solution will satisfy both of these. There's no error introduced in going from the differential form to the integral form. The integral form, the advantage is that I can apply it to control volumes, cell by cell, and derive algebraic equations relating cell center values. And in the process, I introduce an error, the discretization error, and intuitively, you probably can sense that this error can be minimized by using more cells, i.e. refining the mesh. And these algebraic equations, you can think of them as algebraic statements of conservation. But then these are nonlinear. In our case, the momentum equation is nonlinear, so we have to solve it iteratively. So what you have to do is you have to linearize these algebraic equations about guess values, and in the process you introduce a linearization error. And to drive that linearization error below a tolerance, you have to solve iteratively, updating the guess after each iteration. And how do you know when to solve the iterations? You stop when to stop the iterations. You stop them when your imbalances, mass, momentum, energy imbalance are below tolerance. So if you think of the algebraic equations as blah is equal to 0, if I had the exact solution to the algebraic equations, the right-hand side would be 0. But I don't have the exact solution. I have an approximate solution. The right-hand side is not going to be is going to be different from 0, and that difference is related to the mass imbalance or the momentum imbalance, and so on. So that's a whirlwind tour of the finite volume method, and I'll go back to some of these ideas when we are in implementing the solution in Answers Fluent.